Welcome to lecture 8 of 224D. So, the problem set 1 was already due, and hopefully we're all on top of it. So thanks so much for the feedback on the class so far, that to the people who've given it. I've had 52 responses, so it's probably a good subsample. I'm happy that compared to last year, I think we had roughly 1/3 of people for whom the speed was right, 1/3 was too slow, 1/3 was too fast. We improved a little bit over that, so we're 2/3 of the folks think the speed and the lecture complexity is just right. So I'm happy to hear that. There is still 1/4 of people who think the lecture notes were a little too fast and a little too hard. So today we'll do a little bit of recap. Also, there are a couple of other pieces of feedback that were really great to see, and I'll try to incorporate them starting today already. Some folks want to see more of the intuition behind the math and models, so there will be a lot more of that today. We'll go through another toy example, which is another piece of feedback that people want to see more of. And then next week I'll do also a recap session of all the most important concepts. Yeah, there will be a nice sort of high-level intuition, for instance, today of the problems that we may encounter when we try to train recurrent neural networks, and then some intuition and math to fix it. One student was worried about the vectors being, having different dimensionality, row versus column vectors. In theory, all the vectors on the class should be column vectors, so whenever I did mess that up, let me know. It's very possible that I did, but in theory they should all be column vectors. On the problem sets, there are some people who just didn't like them but didn't give quite constructive feedback. A lot of people, I think the majority of folks, liked it, which is good. That was also because last year the first problem set was one that we did last year. The next ones are going to be new. I don't think there's been ever a class yet that used TensorFlow for the problem set, so there's very little for us to learn from the mistakes of others. So bear with us. If there are any issues, do let us know on Piazza, and we'll try to fix them. We tested them quite a bit with me and the TA teams, and we went over them, but I'm sure there's still some small issues that crept in. We're trying to also add all the dimensionalities. That was another piece of feedback. Some folks got tripped up on the dimensionality of inputs and outputs. It partly is something that you should know from the math, but we can also make it easier by providing that in the comments, and we'll try to do that for this and the next problem set. And then another major piece of feedback was that people would like to see a list of proposed projects, and I actually think that's a great idea. So I asked a bunch of research groups at Stanford, mostly NLP and the deep learning groups, to see if they can come up with additional ideas, and then everybody who came to office hour and asked me, I gave some ideas, but I might make that more easier and basically compile a list and tell you. So in order for that to still have any useful impact, I'll move the proposal deadline to next week, Thursday, so today in a week, so that you have some time, and on Tuesday we can go over a list of potential projects for those of you who haven't had their own ideas yet. Those are just going to be proposals. It's very much encouraged that you have your own ideas based on your research or your interests, and you can do whatever you want. Also, there's one question around whether the extra credit deadline for the data set and having a first baseline was for the proposal or the milestone, and it's the milestone, so not the proposal. You don't have to have already a data set and the baselines figured out. But we do encourage you to do that once you have the milestone deadline. All right, are there any other questions organizationally, or? Hopefully tonight problem set 2 will come out. We tried to run it on some of the clusters on the Stanford campus, and there's some issues, so we're trying to iron those out. Yeah.
Do we all have access to all the clusters? Or?
that's the thing. I don't think everybody has access to all the clusters. So I think there's some from the different departments, but we want to make sure that it works smoothly for as many of you as possible.
Did you guys pre-install TensorFlow?
Yeah, we did. Yeah, you would. Otherwise, you'd spend the first month doing that. So we've been working with the infrastructure folks who've been very supportive. But then it's also non-trivial sometimes to install TensorFlow. And it's installed locally. But if you just import TensorFlow STF, it should work on most machines. But hence the slight delay. Cool. All right. So trying to bring the folks, the 1/4 of people for whom it was a little too fast, up to speed today. Last lecture, I wanted to make sure we have at least an idea of recurrent neural nets, because we were thinking the problem set would come out, and we want to make sure you know sort of the high level of the model. So today, I'll take a step back and walk slowly through some of the concepts of recurrent neural networks, of language models, tie it back, give some examples from natural language processing, so that you really get a better intuition of why they're so useful. And then we can deep dive into the problems that you will encounter when you try to train them in a variety of ways. And then we can actually start extending the baseline recurrent neural networks. Once we understand them, we can go to bidirectional ones and deep recurrent neural networks and so on. So it'll be very exciting, because those are models that are very viable and useful for you to use in the rest of your life, but also in the projects. All right. There are no further questions? Cool. Then let's talk a little bit about language models. We kind of breezed through that at the end of last week's lecture. So main recap, we want to compute the probability for a sequence. And I mentioned that this will be useful, but here are a couple of real examples. Let's say you try to have a machine translation model, and the machine translation model comes from French, for instance, where sometimes adjectives are in front of nouns and sometimes they're behind nouns. And now your translation model might give you two potential candidate translations from French. And one might be the cat is small, or small the is cat. And now you want to basically know that one is a much more likely sequence than the other. So the cat is small, the probability for that foregram should be much higher than of the sequence small the is cat. Likewise, in translation, you often have certain words that can be translated into different words in the other language. So for instance, home and house might be the same, might be both possible translations for Hause or house in German. And so if you have the possible translation walking home after school versus walking house after school, then to English speakers it's very obvious that one is a much better translation than the other. But to a machine translation model that just co-occurred and counted how often do I see this word next to that word versus not, it might be less obvious. So it's useful if we have basically good probability estimates for sequences. And you can think of similar things when you have speech recognition, where you say, I want to know the price of wood. And now wood, the default and the times you most often see wood is in the sense of like, I would like to do something, that kind of wood, and they sound very similar. And so a language model might help you and tell you which of the wood is more likely given the sequence of other words in front of it. So generally, those were approximated, because it's very hard to compute the entire probability distribution given all possible sequences of the English language, for instance, or other languages. And so we'll use an obviously incorrect but necessary Markov assumption in traditional language models, where instead of predicting the next word based on the entire sequence of words before, where we would have to keep a very large table, we'll basically just look at the n words before the next word we'd like to predict. So this is an approximation, very common one, but it's obviously not a true one. The next word of a sentence, or the next word that I might utter, will always depend on a lot of other words that I've said before. And so when I was talking about computing counts, this was basically what I was saying. So here, let's say you want to get the probability for the next word after the first word, and let's say our window n is only 1. In that case, for just basically looking at unigram or bigram probabilities, we will only look at the counts of how often do we see the sequence W1, W2 divided by how often do we see W1 by itself. Now we can basically go through all possible words that we have in the English language, and we create a very large table where we look at how often do we see the words in this sequence versus how often do we just see W1. And we compute that very, very large table. Now, that will not be a very accurate estimate, right? If I just know that the happened before, a lot of different nouns might follow. So another way we could do it is extend this to bigrams and eventually trigrams. So here we have a simple bigram model, so we condition the probability of seeing a third word based on the preceding 2 words. But now we need to collect all the counts in our entire corpus for every possible sequence of trigrams. And there are a lot of trigrams, right? So if the English language has at least 50,000 to 100,000 useful words, so that's 100,000 to the power 3 many possible numbers we now need to collect and keep around, even at test time, to compute that probability of just a single word. And in general, we want to have not just conditioning on bigrams, but ideally tri or 4 or 5 grams. And we know that the performance improves the higher n is in these n-gram counts. And eventually, we want to not just condition on the 4 grams, because maybe there is no 4 gram that you've ever seen at test time, so you might want to do so-called back-off, where you smooth your distributions based on 4 grams, trigrams, bigrams, and unigrams. But the problem is there are a lot of those n-grams, especially as n gets larger. And so there's a paper by Heffield et al. On scalable modified Knesser-Ney language models. Knesser-Ney is basically just a way to combine the probabilities of all the n-grams with n-1, n-2 to unigrams. And so the best thing they could do after a lot of very low-level optimization was to have one machine with 140 gigs of RAM, trained for 2.8 days, and built a single model with 126 billion tokens. And that's basically a huge requirement. So you could never run that kind of model on your cell phone, right? So here come neural networks, where now, in theory at least, we will hope that every state here captures all the information from the past. Of course, in practice, that isn't really the case, and we'll find ways of making that a better approximation and more true. But at least in theory, we will hope that the hidden states that we compute at every time step in a recurrent neural network will capture a lot of the history that we've seen before. And the main reason we call them recurrent neural networks is that we will actually tie the weights at each time step. So there's no bound of how many time steps we could compute these hidden states for. And the nice thing here is the RAM requirements will only scale with the number of words, times maybe 100. So instead of having to keep around the number of words to the power of 3, 4, 5, it's only 100 if we have 100-dimensional word vectors times the number of words, plus a couple of the weights here that we have to also keep around. And y will again be our output. So then we walk through a couple of different visualizations and the straight-up definition of this. So here we essentially assume for now that at every time step we have a word vector that we now can compute. And we will compute a hidden state here with a simple linear neural network, where we basically have hidden connections from the previous time step and the hidden visible connections or hidden input connections with W superscript Ajax. And then the softmax is again just a simple classifier that we now all know how to derive the derivatives of. We know how to backprop that into a neural network, and we can predict any class that we would want at each time step. So the class could be, in the case of language models, the next word, but the class could also be the sentiment of the sentence so far. And the class could also be the label of that word at that current time step. Lots of different things you could train this on. That's why it's such a powerful and general model. In the default case for RNN language models, it'll just be the next word that we're trying to predict at each time step. Awesome. All right. So again, main idea, we use the same weights W, and we'll run into trouble with this, but it makes it nice because that way we can essentially extend this model to arbitrary length sequences. And again, it's very important to define the proper dimensions. So here we will define D subscript H as the dimensionality of our hidden states. So W superscript HH will be a DH by DH matrix. WHX will be a DH by D matrix, where we define D to be the input, the dimensionality of our word vectors. And in WS, in the case of language models, we'll have the size of our vocabulary, many rows. So this is a very large matrix if we have a lot of words. And then we basically want to predict here the probability distribution over the vocabulary at each time step. So our y hat here is defined as just the probability, again, of the next word, but for all possible word indices. And then we can compute our the same cross-entropy loss function to predict the words instead of classes. So this used to be the sum over our classes, and now it's just the sum over the vocabulary indices. And YTJ is basically the ground truth that we have in this current mini batch or at this time step, and J is the index of the correct, that should be the correct class. And then, well, yeah, so this is the ground truth. In most cases, this will be 0. So this is YTJ, and then Y hat is the actual predicted probability for that class. And then just a lot of people, instead of taking this as the final evaluation, because here training looks very similar to testing. We want to predict the probability, we just push the probabilities to be the right, have the right distribution, largely a 0, like a 1 hot kind of probability. All probability mass should be at one time step, and then basically to get to the main number that you'll see in a lot of papers, we just take 2 to the power of the negation of this average log probability over the whole data set. So intuitively, the less perplexed you are, the better the model is. The less the model is surprised to see a specific word coming up next. And you want to basically assign most of the probability mass to the actual word that appears next. But you basically get some credit also for saying, well, probability for next word being Spain might be 0.5 instead of 0.9. That is better than 0.01. Right? So even if you just give probability mass to all the nouns, that's better than not even understanding whether it should be a noun or an adjective, and then having a broader class and a distribution that is less peaked. Okay, so now the main problem with RNNs is that while in theory they should capture all the information of the previous time steps, the fact of the matter is that it's actually really hard to train them to be able to do that. And the main problem comes also from its main strength, which is that we're multiplying the same matrix at each time step during the forward propagation. So we're asking this simple linear transformation plus these nonlinearities to change the state a lot based on any single word that's coming in. And we're hoping that inputs from many, many time steps ago can still change this despite applying the same transformation at each time step. And so as we're trying to take the derivatives here with respect to W at each of the time steps, we'll run into some problems. I encourage you to really go take a 2 time step a recurrent neural network and just derive the derivatives here for instance, the partial or the derivative with respect to w over a certain prediction at time step 2, for instance. It'll be a great exercise. It's very insightful. So let's look at the actual problems that we will get when we try to train this. And they're actually very opposed. So in some sense, it's funny that we may run into both of them with this model family. We, in fact, will have both vanishing and exploding gradient problems. So if you train them vanilla and you try to, you optimize it, you run your stochastic gradient descent algorithm, at some point you might all of a sudden get not a number. And all your derivatives blew up, all your parameters are blowing up, and you're like, oh, did I have a bug? And you don't actually have a bug. It might just be, you might still have a bug, and you should check your finite difference gradient check and see that there is no bug. But then even if you have a completely bug-free code, you may still run into not a number issues. And that's an obvious problem, and if you have it and you see it. The vanishing gradient problem is a little more subtle, and you might think it's doing what you want to do, but it really can't. And so let's analyze what happens here and gain a little bit of mathematical intuition behind the vanishing gradient problem. So at training time, you'll remember we'll get a delta function, a delta error signal that will basically add and backpropagate at every time step. So at yt, we'll propagate a delta into xt, and then we'll also propagate one into further time steps. And at yt plus 1, we'll do that again, and it will basically keep on going. So there should be errors also here into all the past time steps, in theory, all the way until time step 0, when the sequence actually started. Right. And again, it just comes from the chain rule. So let's look at a simple formulation of a recurrent neural network and see what actually happens when we apply the chain rule to a potentially very, very long sequence of time steps. So let's define our R and N here slightly differently. It's actually very, very similar. Instead of defining H as f of that linear transformation, we'll just apply f only once we compute our y hat. And for now, let's not assume that's a normalized probability just for the sake of this analysis, and just assume we have just a linear transformation that gives us unnormalized scores at each time step. And f here is again our nonlinearity, such as the sigmoid or tan h. Are there any questions about this slight reformulation, where we basically just move the nonlinearity from the definition of h into the definition of y? We still have f here, where we applied f also to the previous time step. And because of that, it's essentially the same thing. All right, now let's look at the total error that we have over an entire sequence, where at each time step we try to predict some output. So derivative of our error with respect to w will basically be derivative for all the single errors that we have. Again, this will just be our cross-entropy error, for instance, in the simplest case. You could also have linear regression, any kind of error you can think of. At this could be a max margin error. Doesn't really matter for this analysis. We'll have some error, and to get to the error of the entire sequence, we basically sum up the errors at each time step. So we'll have an output y, and each output y will give us one error signal. Can you raise your hand if that makes sense? For those who haven't raised their hands, can you formulate a question? Okay, so it's essentially we have lots of little logistic regression problems at each time step, but now they're all underneath it. To get to the hidden states that we use for as input to our softmax, it happens that they're all connected and they're all in this chain. It's a long computational graph in TensorFlow language. Yeah?
At each layer, do you concatenate the hidden input of the x, or do you sum them up?
That's a good question. So the question is, at each layer, do we concatenate them or we sum them up? I wrote that down really quickly I think last week, but you can assume that if you have w times this f plus this w times this x, it's similar to when you basically put both of these matrices W next to each other and you concatenate the hidden and the X. So in some sense, it's still just a linear layer, but the inputs are coming from different places. That's a good question. All right, so now let's assume this is our H. Just have W times nonlinearity times our previous hidden state, plus a linear combination of our word vectors at that time step. Now, if we want to compute, so we have this main sum now. Now let's look at the element at each time step t. That will now depend on all previous time steps. So we'll apply the chain rule, and it's a pretty hardcore application of the chain rule, because now you have all the hidden time steps before, and the current time step depends on all of the previous ones, right? So derivative of the error at a certain time step t with respect to W will basically be the sum of all time steps from k equals 1 to the current time step t of this whole expression. A lot of derivatives and basically applying the chain rule to get to the derivative with respect to W in the end, which is inside each of the hidden states that we computed until that time step, right? So intuitive here, we use W at each of the time steps, and so to compute derivative with respect of ht plus 1 here with respect to this W, well, this W appeared here to compute ht and ht minus 1, ht minus 2, and ht minus 3, all the way until h1. So this is really where we have a lot of them, right? Because each of the HTs depends, or the HT depends on each of the HKs that came before it. Yeah?
So the difference compared to what we were looking at before in terms of the back propagation, the W's at each layers actually aren't updated. This is computing all the way back to the first time step and then update the W, which always applies again.
So the question is, the W isn't updated. So the W is only updated during optimization, but you're right, at each time step during your optimization, you don't update W yet. You basically have the same W to compute all the errors at that time step, and then once you compute your gradient, then you can update W again. But it's the same W, and it's not different at each time step. And in all the neural networks that we've defined before, we've had, you know, W1 for the first layer and a different set of W2 for the second layer, and so on. Yeah. Yeah.
When your training centers are different length and you want to do mini batch training, does it is there a way to unify like the derivative?
So that's a great question. So the question is, as you have different length sequences and you try to update all your derivatives, is there some way maybe you can make that more efficient or you can combine them? And the answer is yes. It's actually deep down in TensorFlow, you'll realize that if your mini batches, one mini batch has length like a sentence with 50 words, and then all the other elements in your mini batch have length of only 5 words, then if you send each of those to one CPU or to one core or to one machine, then all the other ones are going to be done, and then everybody else in that mini batch is waiting for that last sentence, and it actually slows you down a lot. So it's very much a computational trick, but it's very useful to have mini batches that are all where each element of that mini batch has roughly the same computational cost. And then there are actually some really hacky ways for people to try to put all of this together in efficient matrix multiplies on GPUs. And in those cases, you actually sometimes even zero pad. Even like doing zero multiplications of matrices and inputs that are all zero, but doing it very efficiently in one block can be more efficient than not doing it and having ifs and so on. All right, now let's copy this last expression here to the next slide. And let's look at this particular output here. the way we'll derive this, and by looking at all these separate elements of the chain rule, is not as efficient as what we would do in standard backprop. In standard backpropagation, we multiply matrices in a much more efficient way, but we can analyze this here, and it'll be very useful to see and interpret what's going on here at each time step. So remember again our definition of the hidden state. Now, in order to compute the derivative of ht at the current time step where the error came in with respect to all the potential hk's that came before it in this time series, we'll also have to apply the chain rule. So here, the derivative of ht with respect to hk will be the sum of wherever that case started, so we don't have to go past that, but starting from k and having j sum from k plus 1 to t, and have the product here of all these different partials. And now, as you compute this, this is essentially going to be a derivative of a vector with respect to another vector. And that means that we have to use a Jacobian. And basically have here, in general, definition of the Jacobian, if you have a vector valued function, which is very rare. All our costs usually end up being a single number, like the whole cross entropy error. So in most cases, our function have a single output. But in this analysis, when we look at this partial here, we'll have to use the Jacobian. General definition, if you have a vector valued output function, is basically that you have a vector for each of these derivatives of f, for instance, with respect to the whole x is basically a vector, a derivative of f with respect to each of the elements of x. But then because f itself is a vector, you basically get overall a matrix with all the partials. So basically you have the cross product. Each element of the output has a derivative with respect to each of the elements of the input. We don't really have to use Jacobians in any of the derivations. So if you're accidentally running into a Jacobian, you probably could have simplified things in your derivatives. Okay, so now let's look at this exact derivative here of hj with respect to all the j minus 1s. Again, this is our definition of h. And so to compute this Jacobian, we'll basically want to look at all the elements of the Jacobian matrix. And when we write that out, it will become relatively straightforward, but you know, it's still a good exercise to go through it. We don't really have to dig again into all the derivatives. There's also one of the feedback I got to not go into all the sub-indices. It's a relatively straightforward application, again, of the tools that we've seen, but one way to describe that very efficiently is to actually combine all of these and write in the end this kind of equation where we have W transpose times the diagonal of f prime, where f prime here is again coming from this element where you see the other matrices inside. And so the diagonal of a vector is basically just a very efficient way to write a matrix of this form, where you take each element of that vector and you align it along the diagonal of the matrix, and all the other elements of that matrix are 0. So basically have this matrix multiplication here. And we're missing the superscripts. Does anybody have an idea which superscript we're missing? So we're multiplying by f prime of the previous hidden state. Okay, well, in our previous definition, we had WHH and WHX, but here we cleverly dropped that superscript. So it's really just this thing, because the derivatives at each time step, they just end at that word vector, right? So we don't need to carefully look at those. And the hidden to hidden are only in this part. There's no hidden to hidden connection here with the input. So this is the exact solution of this set of derivatives. All right, now it's a good exercise to go through. I think if you write down all the different elements, you'll see how you can put it together in the end, and just this is really just a notational convenience to put it together. Yeah, very good exercise to do at home. Now let's look at basically the norms of this Jacobian. So we defined, again, the final solution here was basically this equals this. Now let's look at each of these elements. Basically here we can define the upper bound of these norms as basically the norms multiplied by itself, with each other, I mean. And now we can just define the norm of W transpose to be beta W, and the norm of this diagonal, simple diagonal matrix, as beta H. And those are basically just, by definition, the upper norms, the upper bounds of those norms. Now, the gradient in total is this product of all these Jacobian matrices, right? And each of these is associated with a step in the forward computation until the current time step t. So basically, once we put we try to upper bound the norm of all of these Jacobians multiplied with each other, we can basically get to this final output here, which is our beta W times beta H to the power of t minus k. Right, all the possible matrices, and basically applying this simple upper bound. And now the problem is that these betas could be either very small, in which case we multiply Jacobians and we multiply all of these numbers with smaller and smaller numbers, or they can be larger than 1, and then as soon as they're larger than 1, we multiply a number that is larger than 1 with itself many, many times. And so t can be 1,000, right, or 5,000. So even if one of the betas, or this product here, is only 2, it's to the power of 1,000 if we have 1,000 different time steps. And that's exactly why we get the vanishing or exploding gradient problem. So we basically applied the chain rule on a high level, and we looked at some simple upper bounds in terms of the norms of some of the elements of those chains in the chain rule, or elements of the derivative computation, and that's how we gain some intuition of where the vanishing and exploding gradient problems are coming from. Yeah.
So when you say the sequence length would be on the order of thousands, like are you applying this to an entire body of text?
That's right. So the question is, how do we get to 1,000 for time step t? And the answer is yes, we can apply this to a very long document, a whole book if we want. We can also compute character recurrent neural network models, where we have each time step is basically taking as input a single character only, and then computes a hidden state. And then you can get very quickly to very high time steps, or very long time sequences.
Another question. So I see the problem with exploding gradients, that the locality assumption would be violated. But for the vanishing gradient problem, you would still get a strong signal from the early parts of the sequence.
That's right. That's right. So that's actually a perfect segue to the next slide. Why is the vanishing gradient problem actually a real problem? So again, the error at the time step will ideally actually tell us tell the next previous time step from many, many time steps away to change during backpropagation. So let me give you an intuition. So ideally, when we try to predict this word here, we will be able to modify some signal, like to change based on what the next word is. So let me give you an example here for language modeling. So similar things actually true for question answering and lots of other really hard problems in NLP. Let's say I have the sentence, Jane walked into the room, John walked in too, it was late in the day, Jane said hi too. What does your internal language model say is the next word? John, exactly. So you're able to take all the previous time steps from many time steps ago, and we can make this arbitrarily harder, right? We can say there's a battle in Spain, and now these two clans used to fight each other for many centuries and blah blah blah, and then they met again in the city of, right? And now you can put much higher probability onto all the cities of Spain. in your internal language models. If I asked you, like, give me the best probability estimate for the next city, you'd say Madrid or something. But if you forgot that it was about Spain and just had a lot of other family history, you would forget that and you couldn't predict that. So some people actually make a somewhat, well, it's kind of a fun argument of saying language modeling could solve all of NLP. Like, you can say, here's a bunch of input, I asked you a question, and at the end of the question mark, you need to predict the next couple of words, which are the answer. And you might also say, well, question answering kind of captures all possible NLP problems. What's the translation of a sentence? What are the part of speech sequences of the sentence? And so on. So in some sense, language modeling, if we really were able to predict everything perfectly, would solve almost all the NLP problems. Now, in practice, it doesn't really. But here we see the problem of why we might want Jane and John here to modify over 1, 2, 3, 4, 5, 6, and so on time steps to try to help us predict the next word. Now, the problem is when we actually backpropagate that the next word here is John, and now we multiply the Jacobian and it's smaller than 1, at some point it will, in many cases, empirically, you can get to at most 7 time steps back. And after 7 time steps, the error does not modify anything in our parameter space anymore. Basically, the gradients in almost all cases have vanished. Until then, they're so tiny, they don't change the internal states anymore during backpropagation on the W. And so basically that means the model cannot tell itself that really what mattered back here, you should give some change to your internal state to better predict the next word. And if you had general, simpler, non-recurrent models where you just have an input and you have a lot of deep model, a lot of very deep sequence, you can also get the vanishing gradient problem. It's not as common, but it still will happen. And we'll actually go through a little IPython notebook now. And that's, of course, very problematic. If you have some input, you have a very deep network, and then you try to predict some output, but now the output, actually, as you try to predict an error and you send your error signals down and they don't arrive at the input, well then the models will stay random, right? If that happens right away. And so let's look at a very simple and clean kind of toy neural network implementation and then compare 2 different unit types. We mentioned the rectified linear units already. And look at a very, very simple, it's not really vanishing yet, the gradient there, because it's only a 2-layer neural network, but it'll give you some good intuition, I think. So this is modified from an example from Andre's class in 231N, where we basically, let me zoom in a little bit more, just set up our simple matplot. Actually, just take the one that we trained already. All right. So we just set up our network, some simple plotting function, then we will randomly initialize here a very simple classification problem where we have the blue class, the yellow class, and the red class. And we make it so that it's not a simple linear problem that any simple linear regression or logistic regression could solve. And then we'll define our sigmoid function, the gradient. So this is essentially our f and f prime. And we define the rectified linear activation function too. Here again over the elements. This is always element-wise if it's a vector. Now let's define a simple 3-layer neural net. We have some inputs x, have some labels y that we want to predict. We'll have our step size, the alpha learning rate. We have a regularizer, standard L2 regularization. We'll define here getting all our, from the model, getting all our parameters out of that model. So we have our hidden states, the bias, and our W matrices for each of the linear layers. Now we do simple forward propagation. Let's take the standard case that we looked at a lot more, which is the sigmoid. We have basically sigmoid off, and then simple matrix product times our input x plus our bias terms, and then element-wise nonlinearity applied to it. We'll do that again. element-wise nonlinearity, hidden layer, it's in NumPy with the dot plus the bias term, and then here the final output of our scores. So W3 here is the softmax, or the softmax weights, and we exponentiate them, normalize them to get our probabilities. Now we'll compute our log loss, basically the average cross-entropy loss, just like we did in lots of other examples, and like you will do in problem set 2 also when it comes out tonight. We'll compute the loss coming from our predictions. Y here is also, again, the classes that we try to predict. Then we have part of the regularization that adds. Now just we have basically the regularization just had a regularizer times W each of the Wij's squared. So the derivative is fairly straightforward. It's half times that. But for just computing the loss, that's just the default L2 regularization. Overall loss is from the data plus the regularization. All right, then we can print this as we optimize this. So this will be, at multiple steps. So now we'll go backprop. We did forward at each time step. We computed our hidden states. The hidden states, again, were just hidden layer 2, and the scores, and then the probabilities. So now we go back through the network in our back propagation, and we've derived all of these very carefully. You derived in the first problem set the delta messages that will come in for taking derivatives of the softmax. So that will be the delta error signal that's coming from the scores. And then the derivatives, we also learned, are always the activations that are coming in times the delta that is coming from the top of that layer. So that's the derivative of W3. And then derivative with respect to just the bias terms, or as it often is the case, just the deltas. We derived that too earlier in the class. Now let's look at the simple one sigmoid, because we kind of see more of the equations that we derived carefully. And this is a really nice toy example. It's also on the website. You can carefully go through it. We have exactly the equations that we looked at before, which is W transposed times delta. And then we have times the element-wise nonlinearities. That was the main final equation that we had derived. And we see it here nicely on one line in the code. And then again, the hidden layer times the delta message that comes in with the outer product to get the derivative of the matrix W2. And again, the bias terms, and then same thing again with the final W1 to get all the derivatives. All right, now we'll just add everything from the regularization, update our weights with the gradients, step size, and so on. And then we can also evaluate at each iteration what our training set accuracy is. Again, by just doing a forward prop through network, getting our classes, and then looking at how often we get the predicted class to be actually the true class Y. Are there any questions about the code? I'll walk through it semi-quickly.
Do you all have inputs at the first layer, like for the second layer, if we don't have an input, like
So the question is, do we only have an input at the first layer?
at least like as in the hidden layer, but in hidden layer 2, you are modifying.
So let's look at the forward propagation. So here's forward prop. We basically start to compute the first hidden layer based on the input data x that we get times W1.
For the hidden layer 2, we don't have any input.
So the input to the hidden layer 2 is the output of the hidden layer 1.
Yeah, so we don't have another input like in the recurrent network?
That's exactly right. Yeah. So the question is, how is this different to the recurrent neural net? You're right. So this is a total toy example. This is not a recurrent neural net. It's just a two-layer neural net, and it's just the standard definition of a neural net. And what we'll see is basically a very toy version of the vanishing gradient problems, which is we'll just observe that the gradients that will arrive at the lower layers are already much smaller than those that arrived at the top layers. Yeah, great question. Yeah, that's good clarification. So yeah, this is not a recurrent neural net. Just a very simple toy example of a standard neural net. Thanks. All right, so now we can train this 3-layer neural net. We initialize all our parameters to small random numbers. Iterate a couple times, train it with 2 different types of nonlinearities, rectified linear and sigmoid. Let's focus more on the sigmoid. And then we can basically look at the sum of the magnitudes of those gradients over time. And the main simple observation we're trying to make here is that the sum of the magnitudes of the gradients that come into the first layer are already much smaller than those that came into the second layer. And this is not even recurrent neural net, right? This is just a simple 2-layer neural net. And we already see that they're almost half the size. And they're already relatively small. So now imagine they get halved each time, and you have 1,000 time steps, right? They're basically 0. They're getting close to 0 very quickly. And that's the main thing here. And it's slightly, it's not as bad for rectified linear. And in fact, the rectified linear are just linear once you're not at the 0 stage. So you won't have this problem as much. It won't go down as much. But then if you can think about it, if you take the same matrix W and you have some parts of which are linear, and you keep multiplying the same W with linear things, then you get the exploding, even not even exploding gradient, but exploding hidden states, right? Because at forward propagation, you multiply the same thing, and for all the things that are positive, you blow it up. So rectified linear are not like the simple, straightforward solution that you might think they are. Though they can help, and we'll get to that a bit later. And so just to look at the outputs here, you can kind of nicely see this is the output with the sigmoid. It actually wasn't able to perfectly fit this example right here. And this is the output with rectified linear units. You can see some of the lines here a little straighter because it's a linear element for each of the hidden states. And it very nicely fits this function. So this is a great intuition and a very nice, super simple kind of toy example for implementing straightforward neural net from scratch in NumPy. It's on the website in the syllabus page. All right. Are there any questions about the example? All right. Now, of course, we do actually use recurrent neural nets. So how do we deal with these problems? Well, vanishing gradient problems are much harder to fix, and it's something that we will only learn about next week. Basically, we can't use the same vanilla recurrent neural net definition that we just saw. We'll have to use long short-term memory recurrent neural networks that are much more complex, but also, now that we have the basic Lego blocks, just interesting combinations of those Lego blocks. For the exploding gradient problem, that is something you really have to solve because you can't train them at all if this isn't the case. And maybe one last word on the vanishing gradient problems too. If you think that all you need to know to make a certain predictions are the last 7 time steps or so, then the vanishing gradient problem isn't that problematic, right? It's only the problem if you really want to push the accuracy higher and you think that your problem requires you to understand the entire sequence of the words that came before. All right, now let's look at the exploding gradient problem. Basically, this is a super simple trick. It was first introduced with no mathematical sort of reasoning other than it works. By Tomasz Mikolov, and the trick is, well, whenever your gradients get too large, you just set them to a maximum amount. Problem solved. Now, of course, when you run your gradient check through that and your gradient check hits that and you just clip it, your gradient check will fail. It's not the actually correct derivative, right? It just happens to work incredibly well in practice. So we just have a maximum threshold, and if the norm of our gradients gets above that threshold, we set it back to that threshold. Super, super simple, but makes a huge difference. Then a couple of years after Tomasz Michalow introduced that, Joshua Benjo and his group tried to actually understand what's going on there and gain some intuition. And I really like this paper. It's from just 3 years ago. And again, these recurrent neural networks are super old models, right? They've been around for many decades. But when people say, oh, there's nothing new, it's just kind of taking old neural nets and there's nothing exciting in deep learning, then there is actually a lot of exciting stuff here, right? People are understanding these models a lot better. They come up with lots of tricks to actually be able to train them, and that's one of the many reasons for having this resurgence in deep learning. And it's not just sort of the old connectionist networks. There are lots of interesting new ideas, and this is one of them. So let's look at the super simplest possible recurrent neural network that we could come up with, which is only has a single hidden state. So instead of having h be a vector, it's just a single number, a scalar. And we still have the value of b, our bias term. And we basically try to have a very, very simple prediction problem. And now we can visualize how big the error is depending on where the weight is for that simple prediction problem. And here is basically what this really great visualization shows us, which is there are very high curvature walls when you optimize the objective function. So usually when you take convex optimization, for instance, you always assume you have a very nice bowl and you kind of try to get to the global optimum. And you see this is basically impossible here. And it's a very not well behaved kind of objective function and optimization landscape that we're trying to optimize. Now, when you're here, you have this relatively smooth curvature, and you basically just take small steps for each gradient descent step that you do. And you'll notice here is basically once you hit this point here, this high curvature wall, the standard gradient descent will push you way back very far from this to try to avoid this. But now you're basically way off again from further away from where you started, and you're much worse off because now, who knows what's over here. Now the idea of clipping the gradient and rescaling it is essentially just say, don't go crazy, don't go very, very far away based on what you've just observed. So very, very simple intuition. Yeah.
But if you're actually up in the upper left corner and you see that you fall down a lot and you prevent yourself from falling down, what's the method?
Yeah, I mean, we don't know the entirety of that landscape, but just empirically, that doesn't seem to be the case. There's, you sort of see it here slightly that, it might just keep going up. All right, now there's another trick for dealing with vanishing gradient problems, and it works for some cases, but it's not the final answer that everybody will use. But there are two important tricks. The really important one is we can actually initialize our W's, both the WHH that goes from hidden to hidden, as well as the WHX that goes from input to hidden, with the simple identity matrix. So just that, it seems so trivial, but it took people several years. I came up with this idea in another type of neural networks, actually more general. We'll get to it in 2 or 3 weeks, called recursive neural networks. And then Kwok Lee, a good friend of mine, who's working at Google now, came up, this was 2 weeks ago in a year, sorry, should have updated that. Basically last year with a similar idea. Initially, intuitively, what that means is that whenever you bring in a word vector, as you start your optimization, all that you will do is you kind of average them all in. right? And then you let the model start doing something smarter than averaging. Intuitively, when in this IPython notebook, what you'll observe is that in most cases, what most people will do as they initialize their W matrices, it'll just be random numbers, completely random. So as you take an input in and you project it through one layer neural network, it'll basically be a completely random transformation of that input. Now, what this idea is basically saying is, well, let's not make it completely random. Let's actually just by default average the word vectors as we start to try to compute what a good hidden state is. And then he also actually uses the rectified linear units, and he uses it for sequences that aren't super crazy long. Now, actually, this example here, for instance, is kind of a artificial data set where they try to compute the class of digits. So you have basically digits from 0 to 9, and you have little pictures, let's say 64 or 32 by 32 pictures of that, and instead of running a convolutional neural network, which we all know is the best model, they take a recurrent neural network and then take the input at every pixel as the input at that time step. And they run a recurrent neural network over all the pixels. So you have a relatively, fixed, it's at most 32 by 32 many hidden states. And if you have very small initialization here, or just have this identity matrix, it's not going to blow up. You're not going to have like gigantically long sequences. So you can get away with the rectified linear unit here. And they show that the combination of these two ideas will get much higher test accuracy, and you can train the recurrent neural network to higher accuracies. Now, on a more realistic problem of recurrent neural networks, and really how they started to gain a lot of popularity, is in language modeling. And so again, Kneser-Ney is kind of the de facto standard for language modeling before neural networks came out, and for many people who are skeptical of deep learning, it still is, that basically is a clever way to combine the counts and the probabilities from a 5-gram model and 4-gram model and 3-gram model and 2-gram, unigram and bigram models. And so here we look at perplexity, which is exactly based on the definition that we gave before, 2 to the negative the average log likelihood there, and our average log probabilities. And what we see here is that basically for a standard corpus like the Penn tree bank, the model is less perplexed if it's a recurrent neural network than it is with this Kneser-Ney baseline. Now, all those numbers have since gotten even further improved, but this was one of the first times where people thought, wow, neural networks can actually be really useful. And again here, the RAM requirements of the neural networks are already a lot better than that of these gigantic count-based models. Now, this one is a little confusing. There's backpropagation through time. It's actually they should be the same thing. There's basically a very simple trick, which wasn't that obvious to the authors at the time. But really, as you do your forward propagation, you only have to do one backpropagation to update all your weights. Basically, you sum up all the delta error signals that you get at each time step as you go backwards through the network only once. And originally, the authors of that paper thought that you have to do that at each time step. So at time step 10, you go and you backpropagate your errors all the way to time step 0. Then you go to time step 11 and you propagate all your errors to time step 0, and you go to 12 and you go to, Instead, what you have to do is you start at the end of your sequence, and you sum up all your deltas, and you keep going backwards until time step 0, only in a single pass. Now, one trick that was evaluated and analyzed is to also have so-called class-based or hierarchical predictions. It's not super hierarchical, but so the first step in that idea. And the main idea here is to actually have classes, and each class only has a subset of the words. So at training time, you only need to update the class probabilities, of which there are between 30 to a couple of thousand instead of hundreds of thousands, and then the probabilities inside that class. And so we'll basically compute the probability of the next word given the history. History is now our just hidden state H. In this factorization, we'll first compute the class given the history, and then we compute the probability of that word given that class. So that makes things a lot more efficient. So the minutes here per epoch are basically much smaller if you have fewer classes, and then as you have more and more classes, it gets slower and slower again. Likewise at test time, but basically your perplexity also suffers and the model works slightly less well. But it's a really clever idea, right? Because you again, your softmax has 100,000 words in it. So you always, just to predict the next word, you have to have a matrix multiplication that's very costly of 100,000 times the size of your hidden state. Here, you just have times the size of your hidden state times the number of classes that you have, and then the number of words in that class only. So it's much more efficient. Are there any questions about this? Yeah.
How do they mix the RNN and the KN?
How do they mix? So there are a bunch of different ways. The simplest one is you can just average the two probabilities from both classes. And then you basically, if one thought it had higher probability mass, it'll improve the output and the perplexity a lot. All right, now those were the simplest problem, and really very few of you need to evaluate language models again. It's kind of been one of the most sort of done tasks in NLP. And so there's some higher level, and it's also usually only in sort of intermediately useful task. It's not useful by itself in many cases. And in fact, nowadays, the holy grail for a lot of the projects and a lot of the applications that we'll do is so-called end-to-end training, where you just care about the final thing and you don't have any other objective functions in there. You just train the one thing that you care about, you have a very large data set for it, and you train everything, the whole model, jointly, including the word vectors. Propagate into everything, take derivatives with respect to every single parameter that you have in the model. You only need to train one thing. So let's look at sequence modeling. For some other tasks that are a little more exciting, such as named entity recognition, which by itself is actually useful. There are companies that actually pay you, or you pay them like a cent for every document where you find your named entity tags. There are other fun tasks that we can basically do now with this model family, where we want to predict any kind of label we can think of for a specific word. It could also be entity level sentiment and context. There are thousands of companies that say, if you're a company and you want to understand what people are saying about your product on Twitter, we'll go out and find all the mentions of your company, we'll disambiguate whether it's Ford, the car manufacturer, or Ford, the actor, and then we'll find only those that are the car manufacturer, and then we look at entity level sentiment. And another one that's kind of fun and a little less often seen is identifying opinionated expressions in general. So this is a fun paper by Ozan Irjoy and Claire Cardi from just 2 years ago on basically opinion mining with such recurrent neural networks. So now you can see you're actually literally close to the cutting edge of what real research is doing in the last couple of years. So here they basically want to classify each word as either a DSE, a direct subjective expression, or an ESE, expressive subjective expression. And I'll just give you a real example here. Let's say, for instance, the committee, as usual, has refused to make any statements. So now, as usual is an expressive subjective expression. It basically indicates a sentiment without explicitly saying it. It's like, it's not this is bad, but it's like as usual, and then you kind of get that they're trying to indicate here that they're a little annoyed. And so we're going to use a very common notation. You may actually see that notation if you work on sequence leveling problems in your projects too, which is the so-called BIO notation, the beginning and inside of any kind of tag that you may have that has multiple words being in the same expression, and O is basically it's not any of the labels that we have. So BIO, pretty common notation scheme. again, yeah, tags either just beginning of the entity or the continuation of that entity. So as usual is 2 words, it's 1 ESE, and so we'll have basically give the first word a BESE and the second word an IESE. All right, now the simplest thing we can do is just apply that exact same recurrent neural network again. And now I've gotten the feedback from some folks that it's better to have the exact same notation for everyone, but I also want to prepare you, if you try to read the related materials, you'll see that every single paper often uses its own notation, and they're all kind of the same, but I want you to be able to be familiar with those, and really you'll see very quickly through just using different letters and different notation. But here, basically, we have again X, our word vectors, so that's exactly the same. Now W here is not hidden to hidden, but it's just observed input to hidden, because X is our word vector. Y is now our output label. Similar again as to softmax, but instead of calling it the softmax function, nicely written out as softmax, he calls it G. And now H is again our memory, computed from the past memory and the current word. So this is exactly the same recurrent neural network that we saw in the first couple of slides of this lecture, just slightly different notation. And we'll see in a second why it might help to have this notation instead of superscripts. Because we will introduce now bidirectional recurrent neural networks. So let's say we wanted to predict as usual, and we want to predict usual by itself. Now if we've seen just as and the side from the left, then maybe we're less certain whether this has this exact label, but if we see the comma in front of it, maybe that will help us to make that distinction. So in general, to classify a single word in a context, it's very helpful to look at not just the left context, but also the right context. And that's the very simple intuition behind why we might want to use bidirectional recurrent neural networks. The main difference, there's really no difference. One goes from the left to the right, and one goes from the right to the left. You can basically take your sequence, reverse it, and then run another recurrent neural network with a different set of weights. Simple idea, very powerful. Again, because we can use information from the words both preceding and following the current word that we're trying to classify. So now he uses this arrow to the right for the simple recurrent neural network that goes from left to right, and this arrow that goes from right to left for the recurrent neural network that goes from right to left. And now imagine we had the superscripts with HH, it would get kind of ugly. So that's why he dropped the superscripts and we just use different variable names. Yeah.
So at test time, does he average out the hidden states, or does he just run the 2 networks and then average the predictions?
That's a great question. So the question is, what does he do at test time to actually predict Y? And the answer is in the slide. Can anybody see it right away? Let's try to analyze the notation very carefully. I guess this is not really a notation we described very well before. What do you guess this would be? That's right, concatenation. So the idea that he will use is he will actually concatenate the hidden states from forward and, well, now I can't say backward because that would be, it's not actual backpropagation, it's just a recurrent neural network that goes from right to left. He will basically concatenate these 2 vectors and gives that as an input to the softmax. Your suggestion of maybe averaging is actually not that far off. It would be a very reasonable hyperparameter to try in your model either averaging or concatenation.
So does that mean that when he trains the weights and he's backpropping through Y, he's actually backpropping through that concatenation? And
that's right.
Is the U another weight matrix?
U is the softmax weights.
Oh, okay.
So the softmax weights now don't get, they basically have number of columns, not just D, but 2D, where D is the hidden dimensionality of the hidden states.
You're not applying an affine transform to the hidden layer anymore?
No. I mean, you applied the standard recurrent neural network coming from the left, standard recurrent from the right. They all have their nonlinearities. And then you just have your softmax weights, but those are basically number of rows is the number of classes that you have. So he here has basically 2 classes for each of the 2 types of things he wants to find plus O. So there are 5 potential classes that you might want to predict. Yeah?
So I still don't understand the fundamental reason for having a bidirectional RNN. Is it something like that? Even though we want the state in the RNN to capture everything that has been seen, it truly does not do that. So that's why we need to have bidirectional.
So the question is, why use bidirectional recurrent neural nets? Is it because we can't really keep track of everything that's to the left? The answer is, even if we could keep very good track of everything that's to the left, it will help in many cases to predict a label for the current word by also taking into consideration everything that's to the right. But the recurrent neural net, maybe we don't have enough time to do the switcheroo, but basically at each time step here, you get it? All right. So basically the forward prop here will only be modified by these 2. Sorry, the left to right RNN will only be modified by these 2, but now maybe the words that come right after modify and give us a lot of really obvious signal. So let's say, simple example, you have an adjective that could also be an adverb. He is, okay, can't come up with a good example, but some adjectives can be adverbs too. And now you see, just afterwards, you see a noun. And then you say, oh, like bad. Like he's, well, you could say badly. Anyway, you get the idea. So if you see a noun right afterwards, then it's obviously an adjective. If you see a verb right afterwards, it's an adverb. And so that is a simple way where you don't even need to know all the context from the right, but just the last couple of words to the right, and this model will help you. All right, so H here represents, basically in some sense, summarizes all the past and future around that single token. Now, what if we wanted to make it even more powerful and we actually want to have a deep transformation that every word vector goes through and every hidden state goes through? And this is the final culmination of models of today's class, which is a deep bidirectional recurrent neural network. And now you understand why TensorFlow is so amazing, right? This is just another computational graph with a bunch of nodes, and you just define it with this equation, and now you don't have to manually go in and derive all your derivatives. Imagine how horrible that would be. It would take us probably like 2 lectures just to go through all the indices. So intuitively, it's very simple, right? We have now at each time step 3 hidden layers before we predict the output at that time step. And now each of these will basically have also recurrent connections at that hidden state. Yeah?
So for the input X, are we giving it the raw words codified as like 1 host, or are we giving it word embeddings?
Those are still word embeddings, so they also came from a complex model.
So why would you need to give it word embeddings? Because it seems like...
You're totally right. You don't have to.
Yeah,
you could, in theory, assume that those are 1-hot vectors, and then the first layer kind of brings in the word vector, because if it is 1-hot vectors, the columns of those would essentially be the word vectors.
Right.
You're right. So this is like a monster of a model. Turns out to work slightly better. Now, really quickly, how do we evaluate this? This is actually kind of important. I'd like to go through it a little more slowly. But you basically have manually labeled all these different, at every word you have the ground truth label, and you just look at how often you get it right. The problem is that most words don't have any of the main important 4 labels, the ESE and DSE. They're just O. They're not a subjective expression at all. And so if you just looked at accuracy, if only 5% of all your words are either a direct a DSE or an ESE, then your accuracy is 95%, and you think, oh, this is so great, I'm done. So whenever you have such a skewed distribution, it's extremely important to actually evaluate with F1. So F1, very simple measure. Basically, we look at the precision, it's the total true positives, and we divide the true positives with the true positives and the false positives, and we look at recall true positives divided by true positives plus false negatives, and then we have here our precision recall. We multiply those two and basically get here this mean F1 of precision and recall numbers. And that will essentially balance out, and you can't just say, well, everything is in the O class, I get 95 accuracy, right? That might have high precision, but then very low recall, because you're losing all the ones that aren't that, and you basically average those two out. Now, we can look at number of layers and what helps and for different problems, and basically we'll observe, regardless of whether you have 24,000 parameters or 200,000 parameters, that after 3 layers of depth at each time step, you don't really gain anything in F1. All right, so let's quickly recap. Recurrent neural networks, one of the best models, model families of all of deep natural language processing, likely one that you'll want to use and compare with in your projects. With TensorFlow, you'll be able, in problem set 2, you'll be able to very quickly implement that. Training them can be hard. TensorFlow will automate some of it. You really want to carefully look at your vanishing and exploding gradient problems, especially if you think that the important signal for any prediction you're trying to make at a time step is many time steps away. You're going to want to use more important and powerful RNN extensions like LSTMs and GRUs, which we'll cover next week, and then you're all set for some really cool projects. Thank you. Hey.
I'm running this Recurrent LP with a map reduce.
Cool.
And I'm getting some like error, like exceeding the like GC error.